Okay. Hello everyone. We are starting with problem A. Uh, in this problem, we are given an integer x. So we are given an integer x, and we have two operations that we can do. First kind of operation is if in integer x, if we are able to find two consecutive threes in the integer, like for example, as they gave 1 3 3 2 3. If you find two consecutive threes, then you can pop them out to get the new string 1 2 3. So first operation is like deleting two consecutive threes, and the second operation they gave is if the value of the integer is greater than or equal to 33, then and you can only do this operation if the initially the integer is not equal to 33. And if x is greater than or equal to 33, then you can set x to be x minus 33. So you can essentially remove 33 from x. And the question is, for a starting integer x, if we are able to do any number of these operations to get a final value, to get the final value of x down to 0. So in this problem, if you see, the first operation is kind of redundant, in the sense that if you are removing 33 from any position in the initial string, 1 3 3 2 3, or any arbitrary string, if you are removing 33, so assume this is how this current integer could be represented in decimal form. Then what essentially you are doing is
So we will start with problem B now. In this problem, we have been given two integers n and k, and we have to output a permutation such that this value is minimized. This value is basically the sum of the minimums of all subarrays of length k. So first we observe that any value x at any position, let's say, can contribute to at most k subarrays of length k, because this will contribute each time at each index of subarrays of length k. So any value x can contribute at most k times to this value. So an obvious upper bound to our answer, obvious upper bound to this value should be 1 repeated k times, 2 repeated k times, 3 repeated k times, and so on. And we can actually show that we can achieve this value by a construction. If we 1 index the array, at the kth index we put 1, at the 2kth index we put 2, and so on. At the ikth index we put I. What this array does is, for all subarrays of length k, start from here, we will get 1 k times, we'll get 2 k times, and so on, which was the upper bound to our answer. So this subarray actually achieves the upper bound to our answer, so this must be optimal. This is the implementation of this problem. We initiate our variable by 1, and we iterate through the array. And if the index modulo k is k minus 1, if we are checking k minus 1 because we are zero indexing the array, we just increment the value of our variable. And after this, the rest of the values do not matter. We can fill randomly, and then we output the values. So this was problem B. Now we move on to problem C. In problem C, we have been given a binary string which starts with a 1. Now we have to choose two substrings such that the XOR of these two substrings, let's say A and B, are maximized. So we see observation number 1 is that, let's say we do not choose the whole string as any of A and B. We choose some of its proper substrings. Then the length of this thing would be less than equal to n. And if we had chosen any of A or B as n, as the whole string, sorry, the length of this would be less than n strictly because we have chosen a proper substring. If we had chosen A as the whole string, then the length of this string would be equal to n. If we do not choose B as the whole string, because of obvious reasons. So we can show that choosing the whole string as a one string as one substring is optimal. So we have the whole string as one substring. Now we have to choose one of its substrings so that the XOR of those strings are maximized. So what can we do is, first we observe that the whole string is in this form. First we have a lot of ones, and then we have a 0. Because if we had all ones, the obvious answer would be just choosing the whole string and then choosing one of the one let substring, which is pretty obvious to prove. So we are assuming that we have at least one zero in our string. So let the index of the first zero be k. So, and the string goes on. So if we choose if we have to choose some other substring b, such that XOR of this whole string and b is maximized. So intuitively we can see that the substring b should contain zeros at the first and then have 1, so that the XOR of this and this becomes 1. And then the rest of the strings do matter, but we will see later on that we can check all of such substrings. So we have to choose such substrings such that it has length at least k, and kth bit is set, and all the rest of the bits are 0 after the kth bit. So let's say we are selecting this string, this one here. Here the third bit should be one of whatever strings. Should The third bit should be one whatever string we take as a substring. So let's say we can take this one 110. But since the length of the string should be at least this much to get the first bit to be 1, we have to choose at least this much, right? So If the index of the first zero is k, we have to choose a substring of length at least n minus k. If you're one indexing, then we have to choose at least n minus k plus one length substring. So we can basically check all the substrings of length n minus k plus one and get the maximum of them. This can be done brute force in O of n squared, and since n is less than equal to 5000, we fit perfectly in the time limit. The implementation is here. First, we check if the string is all ones. If the string is all ones, then we just return 111n, basically a substring of length 1 and in the whole string. Now we find the index of the first 0. The index is stored in IDX. This function will be say later on. Now we uh, have this set which stores all the Zord substrings. We'll see later on what this does. We found the length of the string we require as b as n minus idx, since this is zero indexed. Now we see all strings which start with one. This is the substring. We Zord this string with the whole string s, and we insert this string in the set. Then we just pick the maximum element from the set and its index. This XOR function can be written very trivially, just brute force. So this takes O(n) time. This loop runs at most O(n) times, and this is done in O(n) time. This is done in log n. So the time complexity would be O of n squared plus n log n, and we can solve this problem. Somebody's asking, do we need set for storing the substrings? We actually do not need a set. You can just store all the substrings in a vector, and then you can sort it and find the maximum element. And there could be many such ways. Do we need set for?
Hello, is my screen visible?
Yes.
Yes.
Okay, so I'll start with problem D. In this problem, we have some participants and some problems. Each participant has a rating AI, and the difficulty of a problem is BI. And let me take a screenshot. Yeah, so for each k equals 1 to n, for each k equals 1 to m, we have to take floor of m by k problems and make k contests out of them. Sorry, we have to make floor of m by k contests with k problems in each contest and discard the remaining problems. And in each contest, we find the ranking of a participant. Find the ranking of first participant and sum them up. So the ranking is found by taking each other participant which solves more problems than the first participant, and it's given that a participant solves a problem if their rating is less than if the rating is greater than equal to the difficulty of the problem. So let me right. So we solve for a contest with k problems. Uh, We have to minimize the sum of rankings over each contest of the first participant. So for a contest with k problems, we find the problem uh, which for a participant to have a higher rank, for a better rank, then it should solve at least one problem more than the first participant. That means his rating is greater than A1, and there exists a problem such that there exists a problem J such that Bj is greater than A1 such that first participant cannot solve it, and it is less than equal to AI such that the ith participant can solve it. This condition results in participant I being higher ranked than participant 1. So consider the problems of ratings 1, 2, 3 to m. We are assuming that these numbers are in the range 1 to m because if they are not, then we can just normalize this vector. Normalizing means converting a converting a like converting a vector into another vector such that each number is in the range 0 to size of vector and the ordering remains the same. So this would be converted to 0, 1, 2, 3, 4. So here we would also include the ratings of the participants also with the problems because we are comparing them together, so their ordering should also be the same. So we assume that the numbers are in the range 0 to m plus n after normalizing them. So now let's say that a contest has k problems. First, we have to discard m modulo k problems. So consider the let the rating of first participant be A1, then the problems of rating greater than A1 be x1, x2, x3, x4 in sorted order. Then if a contest does not have any problem in this range, then first participant will be the highest ranked participant because no other because all problems are solved by him. Otherwise, only the lowest rated problem matters, which is greater than x given. So we pick the so we have to fix the lowest problem. And once the lowest rating such problem is fixed, all the participants with rating range in this range would have a better rank than A1. So it makes sense to discard the problems which are in the beginning of this array X. So first we discard the first few problems of first m mod k problems of this range, and then we find the problems which are after that. We'll make we'll partition them into groups of k to have them all in one contest. Then the next group of k will be in the other contest because once we have the lowest such problem, let's say we discarded these two. Now that we have this problem, having this problem does not change the number of participants that have ranked better than the first participant. So we find k such problems, add them into one contest, move to the next k batch, add them into the second contest, and so on. And before that, we pre-compute the number of participants that reach higher rank than first participant if we pick a problem of rating x something. So we add Here we add x4 to our sum, and if the second contest starts from x5, then we add like p of x5 and so on. So the time complexity of it would be order of m by k, summation of m by k, which is order m. Let me explain it with my code once. So this is the part where we normalize the two vectors for a and b, form a map, and then make a vector of elements from both a and b, sort it, erase the unique elements, and then map the elements to the ith element in increasing order, and then replace the elements in the vectors with their positioning. This increment vector stores the amount of people that have rating greater than equal to u for each u, such that u is greater than r also. R is the rating of the first person. Then we iterate from k equals 1 to m, discard m mod k problems. Here we removed all the problems with rating less than equal to r because they will be solved by us and do not matter in the ranking. After that, we keep b in the sorted increasing order. So here we discard m mod k problem. So we start with I equals m mod k. And the initial answer would be m by k because there are m by k contests, and in each contest we have a rank of at least 1. Then if I is greater than equal to size of problems, then we have discarded all the problems with which were of rating greater than r. Otherwise, we iterate on I, increase answer by increment bi. That denotes the number of participants with rating greater than equal to bi because this problem has to be added in some contest. Then we add the next k minus 1 problems in this contest, and so we increase I by k, and then we output answer.
Yeah, we'll continue with problem A. Sorry for the network issue. Yeah, as I was saying, the first operation is kind of redundant here, because if you see the first operation where you have some sort of string that is available and there is 33 continuous 337 two threes continuous together, and after doing this operation, assume you have the left part and you have the right part. So the resultant string looks like left followed by right. Now, the kind of invariant that this possesses is that uh, the resulting string modulo 33 remains fixed. So the way you show is like this can be assumed as first removing 33 times 10 to the power of length of right, which is essentially equal to which is essentially a multiple of 33. So that doesn't change modulo with respect to 33. And the left string is being and this much part of the string is being divided by 100. So it's like L times, so whatever this length is, which is 10 to the power of r plus 2, and this is being divided by 100. and that is being added to the resulting string. But if we see this operation, 100 modulo 33 is exactly equal to 1, because 33 times 3 gives 99. So this results in a modulo 1 with respect to 100. So what this means is, like, its inverse modulus is also going to be 1. So what does it mean? Dividing this thing doesn't really change anything with respect to modulo 33. So, like, L times 10 to the r plus 2, this can be written as L times 10 to the r times 100. So you can essentially write 100 as 99 plus 1. So what this means is, like, you are ignoring that 99 part because this is being multiplied by 33, and the resulting that you are getting is L times 10 to the r. So this means that with respect to modulo 33, the resulting operation has not changed. But if we see the second operation that they gave, which is exactly subtracting the corresponding value by 33. So taking modulo with respect to 33, or, like, I mean, this essentially means that you can repeat the second operation as many times as you want instead of just doing the first operation to get the same effect. So directly discarding the first operation, we can only apply the second operation in our equation. So when applying the second operation, we just need to check that if we are repeatedly able to subtract 33 from x and get the value of x down to 0, this means that x initially have to be a multiple of 33. So we just check if x is a multiple of 33, and if that is the case, we say it as true. Otherwise, we say this as false. So that is the solution for problem A. And now we move to problem E. So in problem E, we are given a bipartite graph of which is constructed with the two integers n comma m, and we have two n vertices on the left and m vertices on the right. And we are asked to they said that this is a fully connected bipartite graph. What this means is that there is an edge between every pair of I to j between these left and right sets. So this is like a fully connected kind of set that we are having here. Then the question they asked is that we are given n colors to color this graph, each edge of this graph, and we don't want a mono monochromatic cycle in this graph. So what forms a monochromatic cycle is uh, like you are able to create some sort of cycle in this graph, say for example 1 2, and getting like 1 go to here, go here, and get back here, and all of these edges happen to be of the same color. So assume red, 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 red. So if this kind of arrangement happens, you are able to reach back to 1 using only red edges. So what this means is, like, you have essentially created a cycle in this graph. So they are asking us to find, for a given n comma m, whether it is possible to construct a graph and color the edges using colors only from 1 to n, such that there is no monochromatic cycle formed in this graph. So the way we can solve this problem is like, uh, so first we have to tell whether it is possible or not, and then we have to essentially print out the colors which will form the corresponding graph if it is possible. So the idea of this problem is to rely on the fact that if assume ci represent the number of times the edge I is colored. So what this means is like C1 plus C2 plus C3 plus so on up to Cn has to be exactly equal to the total number of edges in this graph, which is 2 times m times m. So if you see this equation, all of Ci's are positive. What this means is like there should exist at least one Ci such that which is greater than or equal to, like, if you evenly split these terms together, that is the minimum possible value of Ci. So there exists at least one I such that Ci is greater than or equal to 2n m by n, total number of elements. So there exists an I such that Ci is greater than or equal to 2 times m. So now what we show is like, if this happens, we can now we show that if Ci is greater than or equal to 2m, let's imagine this case. So you have n nodes over here, 1 2 3 so on up to n, and you have 2n, and you have m nodes over here. What if you are using Ci number of colors, like what would be the uh, number of edges required in this graph if you were to make a tree, a bipartite tree in this graph? So if you essentially construct a tree, number of edges have to be 2n plus m minus 1. like total number of vertices minus 1. So if in a resulting graph, if there are more number of vertices than this, then you will be creating a cycle for sure. Now, if it happened to be the case that a color Ci is used more than 2m number of times, and it just happens to be the case like 2m happens to be greater than or equal to uh, 2m happens to be strictly greater than or equal to 2n plus m minus 1, or 2m is greater than 2n plus m, then we can be sure that there will always be a cycle, because there are more number of edges than required to form a tree in this whole graph. So there will directly be a cycle. So what this means is like if m is greater than or equal to 2n, there will be a cycle. So if m is greater than or equal to 2n, we directly say that answer is false. So you can't have it. Now, what happens to the cases where m is less than or equal to strictly less than 2n? So what we try to do is like we try to provide a construction where we'll always be able to find such a coloring. So the idea of so one such coloring I can provide you here is, so take up to 2n, take up to m, 1 2 3 so on up to m, and go a zigzag pattern. Assume the first coloring that you are doing with respect to color 1. So make the edges in a zigzag pattern. So you have 1 2 3 4 so on. So the zigzag pattern goes like this. So assume this is how you are coloring with respect to the first color, and this pattern essentially goes till 2n and finally ends at m. So assume all these edges are colored 1. Now we try to represent these in the matrix form. So they essentially ask you to output a matrix 1 2 3 so on up to 2n, and of columns. So these are the columns of this rows of this matrix, and you have 1 2 3 so on up to m. So see the claim over here. So we know that m is less than or equal to 2n. So we try to directly construct a sequence that is like 2n minus 1 in size. For any other m possible m given, you can just output this much set of this matrix out. So I will show you a construction that will construct for the whole n cross 2n minus 1 matrix. And because in the question you are asked only till m, just output the submatrix of size n cross 2m minus 1 from this, n cross m matrix from this. So for the construction for 2m goes like this. So if we try to see, so assume there are two full 2n minus 1 nodes kind of available over here. Sorry, I was essentially giving the construction when m goes up to 2n minus 1. So in this construction, see what is the pattern of these numbers represented. So 1 connects to 1 with 1, and 2 connects to 1 with, and 2 connects to 1 with 1, 3 connects with 3 connects to 2 with 1, and 4 connects to 2 with 1. And you essentially have this pattern over here. So it's like the kind of line that we are forming here. So if you see, this is the kind of line that forms, and this line just continues till the diagonal end. So on up to 2n. This essentially ends over here when you connect this value with 2n. Now the idea is like, think about so if you just move this whole set up by 2 units, what you essentially is like assuming this as the beginning. And if you restart the assigning the values from 2 here, so this is the kind of pattern you will get. Again, another ladder that you are forming here, other stepwise ladder. So you can essentially construct here n steps. So each steps takes 2 values from this set, and 2n steps will take total of so because you have 2n possible values to choose from here, you essentially create n different steps. So all the values over here will be covered from 1 2 2 3 3 4 4 so on up to n. And so the essentially the pattern looks like 1 1 2 2 3 3 so on. It goes till nn, and on the right hand side you repeat with nn here, then 1 1 2 2 3 3, and this just cycles on with n minus 1 n minus 1 n 1 1 so on. So you essentially see that if you agree that this pattern does not create any monotonic cycle of with color 1, you have to also agree that this guys won't create any monotonic cycle because of this shifting argument that we are making. Now because they ask you only to output like only m edges, you can, so what we are essentially doing is like breaking the edges out. So if the whole graph of size n cross 2n minus 1 does not contain any monotonic cycle, the subset of these edges cannot also contain any monotonic cycle. So essentially outputting this subset into the answer will solve the problem. So that is the solution to problem E.
So this is problem F. In this problem, we have two arrays A and B. Each have elements up to 1e18, and we have to we can do this operation any number of times. Pick a subarray L to R, find the smallest element X among B in the subarray BL to BR. Then for each I from L to R, divide AI by X, and we do it in the ceiling division, like we do ceil of AI by X for each I from L to R. So we have to turn each AI into 1 and find the minimum number of operations we can achieve this in. So the constraints are n less than equal to 2e5 and AI less than equal to 118, bi less than equal to 118. Sum of n less than equal to 2e5. So order n log n or something would work, or order n log AI. So first we notice that bi is greater than equal to 2. So if we do the operation 1 comma n 60 times, then all each AI is destined to turn to 1. So the answer is less than equal to 60. This is because 2 raised to power 60 equal to 1e 18, and bi is greater than equal to 2 and a is less than equal to 1e 18. So choosing 1 to n divides each ai by at least 2. So in 60 turns, each ai turns to 1. So this is an upper bound on answer. Next, we observe that if there is an element x and it is the minimum the maximal subarray L comma R, such that this x R plus 1 and x L minus 1 both are less than equal to x. This is a subarray in B. So if we pick x as our minimum element, then it is always optimal to pick this subarray L1 L2R, because let's say that we had picked an array L1 to R1 where L1 is greater than equal to L and R1 is less than equal to R, then we could have increased both of them to L comma R and have the same effect on A, but divide by X another subarray also. Like this region will also get divided by X now if we increase L1 comma R1 to L comma R, because minimum remains the same as X. It does not decrease, and we have some more elements which are being divided by X. So we are closer to turning everything to 1. So this motivates us to form a binary tree where we have the minimum of the array as the root. Then we have left, let this be at index I1. Then we find the subarray, find the minimum element to the left of it, and we find another element to the right of it. The maximal range for the root is the entire array. The maximal range for the minimum to the left of this element would be this till this index minus 1. And the maximal range for the right index would be this I1 plus 1 till the end. Then we repeatedly do this Find maximal ranges for each element, and we have a binary tree of depth at most n. So we let dp of I comma x denote the minimum. So dpix denotes the minimum possible max value we can have in the range denoted by the subtree of I on doing x operations in its subtree. So we have the ranges I less than equal to 0 to n, considering zero indexing, and x less than equal to 0 to 60, because we can convert to 1 at most 60. So we have to find a function to merge these vectors faster. So let's say we have first is the base case that we have only a single element in the subtree. For that, dpix will be just doing, let the index be j. For that, dpix would be aj by, repeat this x times. So now we have to merge these gp using at most two subtrees. For that, we first divide the operations between the two subtrees. Like, we don't do the operation on the root of the subtree. First, we do the operations on the two subtrees. Like, let's say we have I operations to do. Let's use another variable. Let's say we have, let me see what I had used. Yeah, I used I only. Let's say we have I operations to do. Then in the left subtree, we do x1 operation, and in right subtree, we do x2 operations. For that, we can maintain a two-pointer approach. We maintain a pointer I1 for the number of operations on left subtree, I2 for the number of operations on right subtree. Once we increase from I to I plus 1, we check whether dp l comma I1, we compare dp l comma I1 and dp r comma I2. Whichever one of them is smaller, we increment the pointer of that. Sorry, whichever of them is bigger, we increment the pointer of that to decrease the maximum value in that subtree. So let's say that dp l is the left subtree, r is the right subtree. So if dp l comma I1 is smaller, then we increment I2, otherwise increment I1. Then first we make a vector in which v of I stores minimum max value in both subtrees on doing I operations. After this, we do operations on the root of the subtree. So for that, we begin from ith operation. First, we check the minimum of max of the other subtrees, of the two subtrees. Then we add element x to it. X equals ai. Let current node will not be I. Let the current node be z. So x is az. So for transitioning from vi to vi plus 1, Either we can do I plus 1 operations on the subtree and no operation on the root, or we can do I operation on the subtree plus 1 operation on root. So in this case, the maximum value in the subtree would be p of I plus 1 comma x, or and in this case the maximum value in the subtree would be because using I operation in the subtree the maximum value is vi, and we divide everything by bz once in one operation, and we also divide x by bz in one operation. So the maximum value turns out to be this if we do transition from I to I plus 1 in V. So we have the dp values of each node. In the end, the answer will be the first index for which dp of root comma j equals 1. The smallest such j will be the answer. I'll go through my code once. First, I wrote a sectree template to find these, to make this tree. This tree is formed using a sectree template to find minimum element in a range and the index of it. Then we recurse in the left and right side. This function makes that tree. Now this function merges two DP arrays. Sorry, this doesn't merge. This function iterates over the tree and gets the answer. This function merges the two DP arrays. First, I append this is the left subtree's GP and this is the right subtree's GP. First, I append values till 60 such that I don't have any runtime errors. After that, first I make the V array by storing two pointers I1 and I2 and incrementing the one which has the minimum, which has a bigger value. After that, I do the second DP in which I either do operation from Vi to Vi plus 1, or I do no operation on root and do I operations on both the subtrees. So Vi has been Vi comma cur is stored for the previous transitions from cur is stored for transitions from less than I. So we do cur equals floor of cur by I, and then we do Vi equals min Vi comma cur. Earlier we included x in Vi only, so we don't have to include it now. X is the value on the root of the subtree. So this get functions iterates over the tree, gets the value for the subtrees, and then merges them. In the end, we find the first node, first k such that v of x of answer is equal to 1. Then output the answer. X here is root. The time complexity for this is order n times log n plus order n times log ai, because this merge function works in 60 steps, which is equal to log of ai, and the segment tree works in each operation in log of n time. So n log n comes from that, and n log 60 comes from merge function. So that is enough to pass within the time constraints.